Okay, in the previous lecture, we talked about different algorithms that are extensions of the synthetic control method, mostly based on regression, but also balancing. But they're trying to make sure the pre-treatment covariates, including outcomes, are as similar as possible, subject to maybe intercept shift between the treatment and the treated and control groups. So in this lecture, we take a slightly different route. We take the model more seriously and try to model that interactive fixed effects or factor structure in the error term. And there are a couple of different ways to do that. One is the interactive fixed effect model developed by in a series of papers. And 2003, 2009, I think both in Econometrica with co-authors. And then I'm going to explain the matrix completion method, which is introduced by Susan AC and co-authors. It's based on algorithm from computer science, and then it can be used to for causal inference purposes. Then I will try to incorporate both of these methods and also a simpler method into the same framework of what I call not me call, but a lot of people call counterfactual approach, counterfactual estimation approach for panel data. And then based on that framework, we conduct some diagnostics, especially for the presence of time-varying confounders or the implication of parallel trends. And if we still have time, maybe tomorrow, I'm going to very quickly talk about Bayesian methods. One of the issues with all these methods and also synthetic control is inference. The big challenge is inference because we don't know exactly how the treatment is assigned. And it's very difficult for us to think about the repeated sampling in this framework, right? If we only have one very specific treatment for one very specific unit, how can we think about a superpopulation in a repeated sampling framework? And hypothesis testing in a frequency framework is only meaningful when you have such repeated sampling idea, but that is very difficult to think about. Let's say the treatment effect is the treatment we're interested in is German reunification. Can we think of parallel universe or universes in which the treatment is assigned to other countries? It's difficult to think about, but in the Bayesian framework, everything is more natural. You have some prior, you get some data, you build some model, and based on the data and the model, you form a posterior of the counterfactual for West Germany in the absence of your reunification. Then you take a difference between the counterfactual posterior distribution and the actual data, the outcome data for West Germany or reunified West Germany in reunified Germany. That would be the your posterior belief of the treatment effects. So in that way, it's much more natural. You don't have to base your interpretation on a repeated sampling framework. And that's why we introduced the Bayesian method. There are a couple of methods in the literature as well. Of course, the method I work on with co-authors is the most familiar to me, so I'll explain that one to you later. But the general idea is the same. Using the same model, so using some model to make prediction for counterfactual and form posterior distribution for the counterfactual. Then you make inference about the treatment effects. Okay, so recall in the classic synthetic control paper in JASA, the authors uses a factor-augmented model to motivate synthetic control. They use this model based on this generative model, argue that synthetic control is approximately unbiased with this model. Of course, this is not the only model with which synthetic control can work. This is one model based on which synthetic control can give you a good statistical property. This is not the only model, but this may be a good starting point. And I think that the reason why the author chose this model is not by chance, right? It's a very neat classic interactive physics model. And it's also consistent with our idea of strict exogeneity or generalized version of strict exogeneity, because there's no feedback from Y to the treatment assignment. And all the confounding are driven by either differential trend. These are differential trends. Sometimes economists control for these as well, like interact dummies with a set of pre-treatment outcome. Sometimes they do that as well. And differential trends captured by observed outcome. These are also differential trends, but those trends has to be learned from data. Another practice, I don't know how common it is, in econ is pretty common, is to add unit-specific linear time trend or corrected time trend into a panel regression to test the robustness of your fixed effects estimation. So you can see this as a generalization of that approach as well, because this FT, instead of FT equals to T or T square, you allow this FT to be arbitrary. It does not have to be linear or quadratic, can be of different functional form. And then these trends can have unit-specific intercepts, which are those factor loadings. Those factor loadings are unit-specific intercepts. That's why this model is also called interactive fixed effects, because these lambda I are also fixed effects. It's just they're not additive; they're multiplicative and have to be multiplied by. So these time and unit fixed effects are interacted with each other. Okay, and then if you don't account for them, and they exist, and you don't account for them, if you don't have the intuition, you just imagine there are some unit-specific linear time trend, and you fail to control for them, and then the parallel trends assumption simply fails, or the strict linearity assumption simply fails. It's because the units are having divergent trends. Okay, although the trend is a general can be more general than a linear line. It can be fluctuating, can be of a different format. Okay, so the question is, what if we actually estimate this model? In my dissertation, I asked this very simple question and then introduce. What I did is basically introduce what is already there in the econometrics literature, interactive fixed effects, starting to take off. This literature starts to take off into the DID framework, and then ask this very simple question: what if I use this model to make counterfactual prediction for the treated units and estimated ATT? Right, that is all I did. And also prior to my work, about the same time, two other authors also have similar idea and published a paper in IESTAT. The algorithm is slightly different. The differences are very subtle, but we almost work on the same problem at the same time. And the Susan, AC, and co-authors, they extend this to and introduce the matrix completion method. You can see the interactive fixed effect as one special case of matrix completion. I'll explain why. It's just two different ways to regularize the factor structure, the error structure, I'm sorry. In a recent how-to paper, how-to meaning it is not really proposing any innovative methods. There's some tests that I think are new, but it's really trying to tell practitioners, applied users, how to use these methods, how to conduct diagnostic tests. So me and two co-authors, we work on this how-to paper to give people some practical suggestions on how to use these methods. And here, I want to first spoil the result that maybe this is very obvious to you. There's no negative weighting problem. Because why? Because we are not using the treated data to construct a model at all. Right? We never use the treated data to construct a model. By doing that, you lose some efficiency, of course, because the model, you probably can learn something from the treated data. But because remember, negative weighting is a problem when we use early adopters, right, as controls, the treated observation of early adopters as controls for late adopters. If we never use the treated data, we treat them as missing to construct the model. So the treated data would never be used as controls for other later adopters, later treated units. So there's no negative weighting problem. And then once we impute y0, we got yit0 hat for each unit, for each observation in the post-treatment period. We take the difference between the actual data, y1, and then the imputed y0. We have in the individualistic treatment effect at the cell level, right, at the observation level. Then we can impose a uniform weights, or either on the observation or on the unit, to get to the ATT. So we at the same time fix the negative weighting problem. We also fix the variance weighting problem, right? We don't have our ATT, if the ATT is not variance weighted, it's basically the unit weighted, uniformly weighted, the unit average ATT. So that is another neat thing. It's very extremely simple, just simply not using the treated data to make models, to build models, and then you address both issues at the same time. Okay, so the limitation, it's not free lunch. The limitation is that we need both large N and large T. Why? Because you want to estimate, or at least even with matrix completion, you don't directly estimate lambda and FT, you estimate their product. Intrinsically, you're approximating a matrix of dimension T by N using a lower rank matrix. So if we use maybe the lambda and FT is more intuitive to you. If we are estimating these fixed effects, these interactive fixed effects, in order to precisely estimate them, we need, for lambda I, we need a longer T to estimate lambda I. For FT, we need more I to get the trend right? So that's the tricky part. I'll explain to you later that these numbers, these interactive fixed effects, are not individually identifiable because of meaning that by using a small transformation, you can get the same result. You shift lambda I a little bit and shift ft a lambda, their product will still remain the same. But after with some constraints, like fixed effects, right? Fixed effects is the same thing. Added fixed effects, same thing. You subtract the mean, the fixed effect will be different. So they're not literally identifiable. It's identifiable only when you impose some identification assumption. These are not causal identification assumptions. These are parameter identification assumptions. But these are not important because as long as we can get their product right, we can get the UIT right, it's fine. It doesn't matter whether we identify lambda I or ft. But if we don't have long t and long big N, we will run into what you are familiar with, the incidental parameter problem. Right? We have incidental parameter problem in the linear panels. So we will have incidental parameter problem with interactive fixed models. Okay, so again, this very familiar to you. This plot, by the way, is made by the panel view package. Self-promotion again. We actually spent quite some time on making this package. Now it's also available in Stata. This helps you to draw panel treatment status, also the outcome variable. Now we also add a new functionality that you can draw a bivariate relationship between a treatment and an outcome, both aggregate level and the individual unit level. So my philosophy is very simple. Is you need to look at the data first before you do any estimation or make any tables. Or figures are usually more telling, especially figures that are closer to raw data. At least by looking at this figure, I know better where the variation comes from. I know better if I blindly use a fixed model, which parts of the units will be more highly weighted, right? These units will be more highly. These units close to the treatment will be the change of the treatment will be highly weighted, and this unit has a bigger variance of the treatment will be more highly weighted. And this periods, like roughly this period that has more variation in the treatment will be more highly weighted, right? According to what we talked about on Monday. So at least I have some sense if I use fixed effects, which part of the data will be more highly weighted than others, and also where the variation comes from. I also have a better sense of how many effective number of units I have. Maybe if I'm interested in ATT, these are the number of effective units I have, not counting the control. Let's say I use this example again. Let's say we have 1,001 units, and 1,000 of them are control units. One of them is treated unit. How many units, effective number of units do you have? Maybe 2, right? If you use synthetic control, you have 2 units, 1 treated unit, 1 synthetic control unit. No matter how the synthetic control unit is made, you only have 2. But if you run a fixed model, you get very small p-value and very small standard error because the denominator is 1,001, right? But you're inflating your precision. You actually only have 2 units because you're focusing on ATT. So by drawing plots like this, at least you have a sense. So I need to adjust for something, right? It's not crazy that I use a fixed model. That's what I think is the most important thing. Okay, so getting back to the approach, it's very simple. We treat Y1 as missing. We basically in the algorithm delete them, right? We don't use them, and then use the rest of the control observations, not units observations. We also use pre-treatment data for the treated unit to build a model for Y0. Of course, we assume some homogeneity assumption. The homogeneity of the structure has to remain the same, and the structure has to carry over to post-treatment period. If there's always like structural change happening from time to time, there's no way to do anything, right? If the structure is fundamentally different between the control units and the treated units, we cannot do much, right? We have to make sure that structure or the model remains relatively stable. Synthetic control, the same thing, right? Synthetic control, you're assuming the weighting structure, the weighting relationship remains stable for extended period of time. If you don't have that, if you have structural change, the relationship, cross-sectional relationship, have changed over time. So you cannot reliably use synthetic control to draw causal inference. So that in that sense, it's similar. And then we can also use pre-treatment data for model selection, right? We can more systematically use idea from machine learning to select models, especially when you engage with matrix completion or factor models. You have to select the number of factors, or you have to select the tuning parameters. And these pre-treatment periods are natural candidates for tuning your model, or for how to be held out and to test which model has a better out of sample prediction behavior. Okay, then once we build a model, we take a difference at the cell level, at the individual observation level between Y1 and the imputed Y0. So this approach is also oftentimes called the imputation method. However, this is not my invention in any way. I probably have emphasized it more in the panel data structure. In the cross-sectional setting, this has a long tradition. The imputation, back to Heckman in the 70s, a long tradition of doing causal inference with imputation method. For the ATT, you can define ATT in whatever way you want. In this case, so if I define ATT in this way, I put uniform weights on observation, right? So each observation has the same weight in the post-treatment period. But this is not the only way to reweight to get to define an estimate. You can equally weight units. You can give 1, 1, 1, 1, 1 to each unit. So you give uniform weight to all the treated unit. That's also the same. That's also a candidate estimate. In this case, if you do uniform weighting on the observation, the first unit will weight 5 times more than the last unit, right? This will weight 5 times than this one if you put uniform weights on observations. I just want to put it out there. It's your choice, but it's not an intrinsic limitation of the method. Any imputation method, you have to make a choice on what estimate you want. But at least it's very transparent. You're not saying I'm weighting it by the variance of something. The variance I don't even know clearly. This is it's an intentional choice that you make. And we can also now draw the so-called dynamic treatment effects plot much more easily. We don't have to remember we talked about on Monday the common practice in econ and more in other discipline, social sciences, like interacting the dummy variables, time dummy variables with the treatment group dummy variables, and you have to choose a base category, so on and so forth. You have to think about how to define, how to deal with those left out categories, like 5 times earlier, 10 times earlier than the treatment, before the treatment comes. But you don't have these kind of issues with counterfactual or imputation method, because you can simply define them based on the time relative to the treatment. You use one, like here, we can aggregate all 1 together. That will be, we can aggregate the individualistic treatment effect in first period after treatment starts, and that would be the average treatment effect after first period the treatment starts. And then we can also do the pre-treatment period, right? The 0 represents the last period before treatment starts, and so on and so forth. And then once we have that, we take average of those individualistic estimates of tau IT. So of course, in the pre-treatment period, it's not treatment effect. It's basically residual average, right? It's the y for those periods. It's y0 minus y0, and it's not out of sample. It's basically residual. These are residual averages, right? And by looking at the residual average, whether there's a clear pattern of pre-trend, we can have a better guess whether there is likely failure of the parallel trend assumption or the strict causality assumption. So we do this, and for example, if we see something like this, of course, this is based on simulated data, so everything looks very nice. You probably will say, oh, this is perfect. There's no indication. We cannot 100% be sure because the assumption is not testable, but based on the pre-treatment period, it seems that there's not a pre-trend. We also would highly recommend you to add a bar plot below the estimate. The bar plot represents the number of observations for the treated unit, because we care about ATT. This measure is important. This is basically how many ones we have. If we have 5 ones, we put a 5 here. We have 100 treated observations, we put 100 here. Why this is important? Because it gives you a sense of, if you have a huge effect here, maybe it's only driven by a handful of observations, right? That is maybe not very meaningful. And also give you a realistic sense of how many effective units you have, issue that I just talked about. And I can tell you by replicating some of the existing studies at least in political science, a lot of the actually effective number of units are fairly small, much smaller than the sample size. Okay, and the reason why it drops, is because right censoring of data, right? For units that starts early, you observe it longer for under the treatment, at least for staggered adoption. For units that start the treatment later, you maybe only observe them for a few periods, and then the rest of the data is right censored. Same thing for the residual averages. It's left censored. Okay. All right. So if you see something like this, obviously there's a trend here, and we're not talking about testing issues here, right? But you can say, doing this eyeballing the testing, this 95% confidence interval, it's significantly different from 0. There's a problem, but I care more about testing has issues with power. I'm caring more about the pattern, whether the pattern looks like there's a systematic divergent trend. Here, there's a clear sign there's a divergent trend. Then we cannot interpret these effects or this difference as causal effects of the treatment. Right? That's basically the same lesson we learned from joining dynamic treatment effects in using conventional methods. But by doing this, you avoid the negative weighting and the other variance weighting issues. By the way, so some of you may ask, so what's your reference group, right? Do you have an intuition? What may be the reference group here? Of course, there is a reference group. So what is a reference group? So the reference group is actually the, you put a constraint on the pre-treatment outcome. So you adjust for the pre-treatment outcome after taking out the fixed effects, they equal 0. So for each unit, the pre-treatment outcome average residual, they equal to 0. That's your constraint. So for each unit, you have such a constraint. So you're testing against the average in the pre-treatment period for each unit. Okay, you're not testing against one particular period that of your choice. To me, that's a natural choice. That's not a big problem. Okay, so here is a comparison with the current practice based on Angus-Pischke. This is based on their work. I've replicated several papers, but for writing this paper, I need to find a good example to illustrate the method. After replicating maybe 20 papers, I don't find there's a huge difference between traditional dynamic treatment effects, a traditional way of drawing dynamic treatment effects and this way. This is good news because maybe the current practice is not that bad. Theoretically, you can find problems. Several people have find problems. I find in practice it's not a huge problem. So I still would advocate for drawing dynamic treatment effects using conventional methods. That is much better than by compare with not doing it than not doing it. Okay, this is much better than not doing it. Even if you don't want to engage with counterfactual estimation, engage with more complex modeling, maybe you need to, you don't want to spend time explaining to reviewers what we're doing. At least do this, everybody accepts. And I don't find a huge downside of doing this, although I said there are theoretically issues involved. And what Angus-Pischke suggests in the book is to find a reserved category as your base category, maybe 5 years before treatment. And more people in the literature, 80% of people, according to one paper in Econ, are using the period right before the treatment starts as the base category. So normally you would see like a dot without confidence interval right before treatment starts, and then some confidence interval before and after. And then people are eyeballing whether they're significant, and if they're significant in a pre-treatment period, it's a bad sign. So testing is an entirely different issue. I don't think that way to do testing is good. I'm more focused on whether there's a clear pattern of trend, either trend or to be too volatile, as I showed you earlier with 4 different examples on Monday. Okay, so let's proceed to the estimators. This is a model-based counterfactual model-based approach because you have to be very specific about how you want to impute the counterfactuals. But although I said model here, DID is also has a model, right? Fixed effect also has a model. It's not stronger than fixed effect or DID, right? But it's not non-parametric. Because any model you can say, oh, any model ORS has a model, but it works with conditional mean, right? So it's all about what kind of assumption you impose. And step 1, train a model using observation and control. Step 2, compute individualistic treatment facts. And then step 3, just summarize the individualistic treatment facts based on according to the estimate you are interested in. And then in the review paper, in this how-to paper, so we review 3 basic strategies. So one is the fixed fact counterfactual estimator. It's very simple. It's basically using a 2-way fixed fact model as a way to impute counterfactual. And we also incorporate the interactive fixed fact model, what I did in my dissertation. And also 2 other authors are working on this model as well. And matrix completion method, instead of directly imputing factor loading of factors, you can actually impute their product directly from data using a lower rank matrix approximation. And as you will see, these 2 approaches are very closely linked. You can even see this as a special case of matrix completion with a special regularization method. And a few remarks. First, DID is FECT, right? DID is a fixed fact counterfactual where you don't have covariates and you have 2 peers, 2 groups. If you have 2 peers, 2 groups, literally DID does is this, right? So there's no difference between fixed fact counterfactual and DID. There is a difference between fixed fact counterfactual and fixed facts, right? Because fixed effects use post-treatment data to estimate both not only beta, but also the alpha I and psi t, which will potentially cause negative weighting. But DID and fixed effects with two pairs, two groups, they're mathematically equivalent. There's no difference at all mathematically. And both interactive fixed effect, counterfactual, and MC are estimated by iterative algorithms. This is not surprising because the estimation of factor loadings will affect estimation of beta, and estimation of beta will affect estimation of factor loading. The same thing for matrix completion. So that's why you need to iteratively estimate them until convergence. This is actually done. This is for IFCT. This is already done by 2009. This is not our contribution. And matrix completion is fairly already very popular in computer science. So what can you think of an example of matrix completion in the computer science world? So any recommendation system involves some version of matrix completion. Netflix, right, or Spotify. You don't normally one user. Well, for sure, no user can watch all the Netflix shows on the platform. So there are a lot of missing data. You don't know whether you like it or not like it, but you watch some and maybe you like some based on your behavior. And then your behavior has some correlation with other users, and using other users' likelihood to watch another show, you may be predicted. You're predicted to prefer or not to prefer this show. This is matrix completion, right? Of course, you have to achieve this. You have to have a fairly complicated distributed system because there are so many users and there are so many shows. Okay, so another thing need to be mentioned is there are tuning parameters involved. So you have to choose tuning parameters. We use cross-validation to choose tuning parameters. And the Bayesian world is much better in the sense that you don't have to choose tuning parameters. You can build a hierarchical model and then let the data to choose tuning parameters for you, right? Doing model averaging across different number of factors, for example. There's another reason why a Bayesian approach is appealing, but the problem with Bayesian the approach is more slow. It's much more slower than the machine learning type of approach. Okay, so in my early work, so you have I just want to give you some illustration. You can write a model this way, and there is a treatment effect here, but I wrote it here without loss of generality because it can be arbitrarily heterogeneous, right? So this equation is almost redundant. It's just definitional. Here, because it's a regression method, it can take in time varying covariates. Time invariant covariates, different from synthetic control, time invariant covariates will be absorbed by the fixed effects. Okay, so, but you can take in time varying covariates. Usually my experience has been those time varying covariates are not very predictive. So those factors are much more predictive because it takes in information from the past outcome. Okay, so let's ignore for the moment the time varying covariates and additive fixed effects. Why? Because additive fixed effects are special cases of interactive fixed effects, right? Is that clear? Because if you keep ft as constant, this term is additive fixed effects. If you keep loading to be a constant, this term will be a time fixed effects. So additive fixed effects are simply special cases of interactive fixed effects. The reason why sometimes I may want to enforce or impose to additive fixed effects is because if you look at the data, if you draw the data clearly, these additive fixed effects has a lot of explanatory power. So by assuming that they exist, you gain some efficiency. Right? You don't have to let the model to learn that they exist. Essentially, you assume that in one of the FT there's a one here, right? There's a constant here, so always here. If I tell the model based on my prior that they exist, the model will be slightly more efficient. But with a lot of data, that doesn't matter. You don't have to assume. You don't have to assume additive fixed effects. Okay, so what it actually does, let's use some illustration. So again, we have this n by t data, right? The x-axis is the time dimension. The rows are the unit dimension, and we have a bunch of units. This is almost like a classical DID. I just use this for illustration. And these parts are what we want to learn, whose counterfactual we want to learn about. And we use this part to test for testing or for model building, for both model building and testing. So what do? We first just ignore, just throw away the treated data for the moment. And then we do a dimension reduction for the treated data, for the pure treated data. So the pure treated data is uncontrolled by T. So let's say for simplicity, we run a PCA, right? We run a dimension reduction method like PC or other factor approach, reduce dimensionality from uncontrolled by T to R by T. So it's like R can be 2 or 3 imagined. So it's like 2 or 3 trends. And then once you have that, you also have data which is untreated by T0. Now you have the reduced dimension, what we call the factors, and you learn the factor loadings you basically run a regression or matching or whatever to learn the factor loadings lambda I for these guys. Let's say the simplest way to running a regression of this data on the factors, and then you get parameters for each factor. Those factors are the columns in the regression. Just like best subset or constraint regression, you have original YT as your regressor. Here you use your factor as your regressor, then get lambda as the parameter. And then you build again, now you have FT. Now next you learn lambda I. So you have lambda I from the pre-treatment period from the treated, and then you have FT from the control, right? Lambda I from the treated and FT from the control. Then basically you can impute the counterfactual for the treated in the post-treatment. And in the post-treatment period, you basically have that, right? That's your counterfactual estimation. Of course, I'm oversimplifying because in reality, you can use the so-called EM algorithm to do this iteratively, not separately estimate them, but estimate together using expectation maximization algorithm. For those who are familiar with, you know what I'm talking about. But for those who are not, don't worry, it's not that different. The result will not be that different. Yeah, you can use expectation maximization. And we make, okay, so once we got that, we calculate, once we got the tau IT each hat, we take an average and condition on DIT equals to 1, and that would be our ATT estimate. I'll give you an example on election day registration or voter turnout. Election day registration is an institution in the United States, in some states, that allow voters to register on the same day of voting, which is considered as a way to reduce the cost of voting, especially increase cost for increased turnout for minority voters and low-income voters. So these are election by year, sorry, state by election level data. The y-axis is turnout. So we have a bunch of controls never adopted EDR, and we have 9 states that adopted EDR at different time points. And pre are in orange and post are in red. So just by looking at the data, you know DID cannot work, right? If you take an average of the control and then take a temporal average of the control and take an average of the treated, of course there will be no parallel trends. That's why we need to fix them. And again, the treatment status plot is like this. You know, this is where the variation comes from. I'm making inference about ATT. There are only 9 states, so the ATT will be very imprecise. Something to keep in mind. And we are here using Rubin's language. Causal inference is a missing data problem, literally, because we literally drop this data and then impute y0 in this period. So this is difference in differences. If you difference in differences also assumes a model, as I said. You're basically taking an average of the control and then adjust for the intercept. This is what you would get from a difference in difference counterfactual. Suggests that EDR actually reduced turnout, right? Allowing people to register on the same day of voting actually reduced turnout if you use the DID. Of course, the pre-period is pretty terrible. If you use the factor model, Connecticut, there's no effect. So we fit the data using the pre-treatment data, and then we look at the counterfactual the outcome. There's almost no difference between counterfactual and actual. Maybe for that state, there's no effect. And then for New Hampshire, it's pretty noisy, right? Maybe it's caused by other issue that is not captured by the model. So I have a lot of caveats about this method because information, so this same threat to DID can be a threat to the type of model, right? The bundle of treatment happens at the same time that is not captured by the model will confound these effects. So the main results, if you use a fixed effect counterfactual, which essentially is DID without negative weighting, right? This is very close to DID, but with step adoption, it fixed the negative weighting problem. So it's DID without negative weighting. You compare it with the factor approach. This is your comparison. The pre-treatment period looks much better. And then the post-treatment period, you have your estimate is by like 3 percentage point increase in turnout, and not significant because the noise of the data. But it's more credible than what you find here, I think. Okay, And what is, to me, what's more interesting is the what's behind the curtain, what's behind the scene, how the algorithm actually works. It identifies two factors. Again, these factors individually, they're not interpretable, but you look at the patterns, they seem to indicate something, to point to something. One factor is a sudden increase in turnout around 1965. Can anyone tell me what's going on? And another factor is a decline of turnout in the past 3 or 4 decades. Can anyone tell me what this is capturing? Sandy is exactly right. It's a Voting Rights Act, right? 1965 that removes, at least on paper, a lot of the Jim Crow laws in the southern states. And if you look at what's interesting, to look at the data, this factor is capturing these things, right? And these states are the formerly Confederacy states. So we're, even if you put dummies for those southern states, you probably cannot estimate it that well. And if you look at the factor loading, the loadings that are big on the first factor, on this factor, are those underlined with red color, are exactly the 11 states that were in the Confederacy, for those who know the context. So basically, the factor model figures out something maybe a casual observant of or casual analyst who know not very little about American politics don't know, and capture this changing trend in a subset of states. That is what's pretty nice about this model. And this model is extremely simple, right? The factor model is extremely simple, even only using PCA. Luke Stanford, grad student, now an assistant professor at Yale Environment School, he applied a similar approach to, or this approach, by the way, what I usually, when I graduate, I call it G-Things. For marketing purposes, I talk to my advisors, to be honest, I talk to my advisors, and then how should I name it? They say you can name it a generalized synthetic control. Okay, so I follow their advice. And then in the paper, I say, oh, this is based on causal inference based on interactive space model. I try to be as honest as possible. But after a few years, now I think this is an improper name, because as you probably have found, this is very different from synthetic control, right? Synthetic control is more about non-parametrically finding the weights and then constructing the convex weights on the controls, right? It's more about the matching or balancing. Well, this approach is more model-based. So I think it's not a proper name, looking back 5 years later. So now these days I call it counterfactual estimation based on interactive space model. I think that's a little more literal and more precise name. And then, so Luke uses the same approach. Later, I think that last year he actually improved the method, not only to combine this outcome model with a balancing with a model for treatment assignment, so have a doubly robust estimator, which we'll talk about tomorrow. But in the first version of this paper, I think he already got the result pretty much right. The later improvement does not change the main result. He applied this method to remote sensoring data. So he asked whether property rights leads to improved land quality in Benin. So the experiment is that NGO gives, I think that the government gives peasants in Benin land titles. And the question is whether having a more secure property right, whether this will change the peasants' behavior in terms of the choices of crops or plants. Luke finds that after getting a more secure property, the land titles, the peasants will start to grow more perennial crops like trees than annual crops. So because you have a longer time horizon, right? And how does he do that? He uses G-Things or interactive space counterfactual model to construct the counterfactuals, at least in the first version. So this is the treated site. The problem with that experiment is that you only have the treated villages. You know the location of the treated village, but you don't know there's no randomized control. You have to find your control. Every village close by potentially can be your control, but you don't know what exactly is your control. It's not randomized. So this is so for image like this is clear indication of perennial crops of trees like orchard. And you can transform this. He did a lot of work in transforming this data to readable format. There are two very close lines, and this NDVI measure is a measure of perennial plants. They have a different way of reflecting the sunlight. And sorry, this is the pre-treatment period. This is the post-treatment period. You see a sizable difference. It's actually pretty big. This is raw data. If you look at the average, it's pretty significantly different. In places with land tenure, peasants are much more likely to grow perennial plants instead of annual crops. And this persists a couple months later. And if you look at the factors, this is like a geographic plot of factors. It captures some seasonal effects. And these are the, let me see, yeah, the color closer to, so these are different loadings of different factors. And you can use inverse weighting method to collapse the multiple dimension of weights into one dimension. And color, those red dots represent the treated villages. Okay, so green means more dissimilar. So a warmer color means that the weight is higher and more similar to the treated units. So this is basically what you learn from a factor model. It can try to find you in a geographic sense, your proper control. Okay, so matrix completion, 2 minutes left. It's actually very similar. Instead of, because our main goal is to predict 3D counterfactuals, matrix completion is doing that. So try to fill complete matrix with missing data. The missing data are caused by our causal inference effort, right? It's not because the data are originally missing, it's because we want to make causal inference. We drop those data for the moment, so they become missing data. In this paper by Sudanese and co-authors, I'm very happy that they treat my paper as a special case because after reading this paper, I tell you, I have no idea where what I was working on can fit into the bigger picture, and now I can see it, so I was very happy about it. So this is another, that's why I think it's really important to draw those plots, like those treatment status plots, because you know where your variation comes from. For those states, this is looking at de facto democracy on state capacity. Those post-Soviet states, there's no variation in treatment status. They born democracy, they remain democracies. If you run a fixed regression, they will be simply dropped, but they will contribute to the counting of the numerator denominator. So that's why it's kind of important. Let me actually see how much time I have. Do I want to finish this? Yeah, okay, maybe I'll pick this up tomorrow. We'll have more time. All right, so welcome to the third lecture of Causal Inference with Panel Data at WashU. In the first two lectures, we talk about first how to think about conventional panel data methods like the difference in difference and fixed effects. And from a design-based perspective, what may be the problem, especially with what does the strict exogeneity assumption imply? That's the first lecture. And then in the second lecture, we talk more about syntactic control methods. And from an algorithm perspective, it's possible extensions. And then we talk about the model-based approach, including interactive fixed model, using interactive fixed model in a DID setting. And then I try to fit this into the framework of a counterfactual estimation in panel data. We just finished discussing interactive fixed counterfactual model, and then now we transit to discussing matrix completion method, which can be seen as a generalization of interactive fixed model in panel data. Because as I said last time, with matrix completion, we are trying to fill in the missing data caused by treatment, right? We treat treated observation as missing data, and then we try to impute their counterfactuals under certain assumptions. And here, what makes things much simplified is the fact that we have a version of the strict exogeneity assumption. We only, for each observation, we only have y0 and y1. And this is not without assumptions, because basically the history doesn't matter much, right? You don't have carryover effects from past treatments. You don't have feedback, and the past treatment history does not affect your potential outcomes. These are assumptions required for these type of methods. If your current potential outcome, the potential outcome at time IT, is dependent on the entire treatment history till now, then the problem will be much more complex. Okay, so let's first finish the matrix completion method, then we will delve into diagnostics, because diagnostics is really important with panel data, because as we have seen, there are so many assumptions involved. All right, so I'll talk about this. And recording the DID setting, we have a missing data problem, but the problem is relatively simple. We only need to impute the average of counterfactual for the treated units in the post-treatment period. We use a very simple way to do that imputation. With matrix completion, we try to find a row rank representation of Y. So Y is of rank, right? The smaller number of T or N, right? We have a T by N matrix. So the rank is smaller than the smaller number of T by N. And then if we can find even a lower rank representation, the rank can be 2 or 3, depending on the number of factors, right? If you have a two-factor model, essentially you have a rank 2 representation of the matrix. You use this matrix to fill the missing data in the outcome matrix. And that's the basic intuition. And in this paper, so the NCA co-authors, they generalized what I wrote in my dissertation with different ways to construct the lower rank representation, which is L. Plus, the missing data can be arbitrary. So in my early work, I imposed a staggered adoption assumption, or I require the treatment assignment to be cannot be reversed to simplify the problem. So when you have staggered adoption, you're essentially comparing a limited number of treatment history, right? And with that, the comparison is much easier, and you can actually allow carryover. You don't care about carryover effects because they're lumped into the comparisons of several treatment histories. But with treatment reversal, treatment switch on and off, we have a much difficult problem. You have to, in order to identify the treatment effects or average treatment effects, you have to impose more assumptions like no carryover or limited number of carryover. And but if you are willing to impose these assumptions, the matrix completion method can accommodate reversible treatments under strict exogeneity. So mathematically, we write our model as YIT equals to LIT. LIT is a low rank representation of the M by T matrix. And then we also can allow additive fixed effects and the influence of observed time varying variables, and then an error term. So we need regularization, right? Because the regularization is required because the dimension of LIT matrix is M by T, right? So if we don't have regularization, we run out of degree of freedom with data. We have data M by T. In the ideal case, with no missing data, we have M by T observations. But LIT matrix is also M by T. That means we want to use less information to impute LIT in order for this to work. There are a couple of different ways to do regularization. So one of you asked in the Q&A, what does it mean by regularization? You see that very quickly. Regularization means I put a penalty on the complexity of parameters. Right? If we allow the parameters in the LIT matrix to be arbitrarily complex, this is basically YIT. So you can't go very far. You can do nothing. But if you require that their LIT, there's a limit for the complexity, the level of complexity for LIT. For example, it has to be, one extreme case is that LIT must be a summation of two additive fixed effects. That is one version of LIT. Then you can do a lot, right? You don't need to use all the degree of freedom in the M by T matrix to replicate or to impute values in the LIT matrix. If you use another factor approach, use a lower rank representation, you don't need that many observations, degree of freedoms either. Okay, so I will be more specific about what regularization means in the next few slides. Here, the objective function, if you just look at the objective function, it's the same idea. We don't use treatment data. We don't use observation and the treatment to estimate the model. The model is estimated using the observation and the control condition only. We'll talk about why we do that, because we don't want to have a negative weighting problem, and we want to get closer to the estimate we are interested in. We don't want to be involved with variance weighting, things like that. So we only use treated data or observations under the control condition to build a model. And we've tried to find this matrix, M by T matrix LIT, such that the difference between YIT and LIT is minimized. And we also put penalty on the complexity of this L matrix. If we don't put penalty, so the best, under this objective function, the best possible model for YIT is YIT. So for Y is Y itself, right? It's the outcome matrix itself. Then it's fully saturated. There's no, well, the auto sample prediction will be very, very bad, and we don't get any interpretation from the model. So we want to make L as simple as possible, such that more degrees of freedom is saved. And you can impose different type of regularization on the L matrix. We can use in the paper, the authors use nuclear norm. Nuclear norm is basically putting regularization on the eigenvalues of the L matrix. Imagine you're conducting. So here, for simplification, for simplicity, we are not we're not discussing covariates or additive fixed effects. You can imagine we simply partial them out. It's slightly actually more complicated than that, because we cannot
partial them out in one step because their values will be dependent on the value of LIT. So it's an iterative process. The estimate LIT, you estimate the additive fixed effects and the beta, and then you subtract them and then you re-estimate LIT, things like that. But just imagine that we have already dealt with them, so we only have LIT for simplicity. Okay, so the sigma I is the eigenvalue of matrix L. Imagine you're running a PCA or SVD of L, and sigma I is on the diagonal of the eigenvalue matrix. And then you can impose different ways to regularize this matrix. One is what the literature called the best subset. Essentially, we have, let's say the rank is T or N, whichever number is smaller. We have T eigenvalues, but the best subset will impose 0 on a large number of eigenvalues. Only the first few eigenvalues will remain positive. Okay, this is so imagine you're running a PCA and you have a bunch of principal components, and you tell the algorithm or tell when you write a paper, tell your reader that I only care about the first 2 principal components. So I keep the first 2 eigenvalues, and I impose the rest of the eigenvalues to be 0. Those will be in the error terms. In annual factor analysis, you're or at least in a non-Bayesian way, you will have to choose the number of factors you want to include in the model. That is one way to regularize a L matrix using a factor approach. And for those who still remember the interactive fixed model, this is literally what the interactive fixed model does. It analyzes the error structure, run a PCA of the error structure, and then keep the first few principal components from the error, and then leave the rest as errors, as residuals. That's one way to regularize L. Another way, maybe a more natural way to regularize eigenvalue matrix is to subtract a number. The number is a tuning parameter from each of the eigenvalues. The eigenvalues will be different, right, from the biggest to smaller to smaller and smaller. And then you subtract one number, a fixed number, which is a tuning parameter, and then keep the positive part as the eigenvalue of the in the SVD. So as a result, if an eigenvalue is smaller than, oh, I forgot I have a pen. Let's say this one, if sigma 3 is smaller than lambda L, and this term will become 0, right? This term will become 0. And essentially, this principal component is ignored, right? And then, of course, all the rest of the principal components will be ignored. Only for those whose eigenvalues are bigger than the tuning parameter, they will remain. But they will remain with a smaller impact on the outcome variable, because what you end up, let's say sigma 1 is bigger than lambda L, sigma 2 is bigger than lambda L, but starting from sigma 3, it is smaller than lambda L. So what you end up having is basically sigma 1 minus lambda L, sigma 2 minus lambda L, and then a branch of 0 on the diagonal. That is what this nuclear norm does. But with best subset, you choose a stopping rule. You stop at 2, and then you keep the original eigenvalues as they are, and then make the rest of the eigenvalues to be 0. Okay. So as you can see from this regularization, these two regularization methods, if the data are truly driven by a 2-factor model, the IFE approach will be unbiased, right? Because there's no regularization on the first 2 factors. If it's truly a 2-factor model, IFE will be unbiased and consistent. Well, MC will be biased because, well, as this is a rule of thumb for most of the machine learning algorithm, if you directly use a predictive machine learning algorithm to conduct causal inference, involves a tuning parameter, there will be some bias remain. You have to correct for biases. There will be biases because you impose regularization on the original data. So the first 2 will also be regularized. But it's a much more softer touch on the regularization. You can allow, much bigger number of eigenvalues or factors into the model, but each factor is regularized a little bit. So that's the difference. So for the best subset, you keep a small number, hoping that these small number of factors have very strong signals. Okay, that's the difference. But in essence, they're the same. One is called hard impute. So this is called hard impute in the machine learning literature, and this is called the soft impute. All right. So what's the pros and cons of interactive fixed-fat counterfactual model? Quite mouthful and matrix completion. So interactive fixed-fat works better with a smaller number of strong factors, as I said, and the matrix completion works better with a large number of factors, and those factors are weaker. I did a little bit of simulation. So on the x-axis is the number of factors. So I imposed a restriction such that the total variation explained by all factors remain the same. So for example, for this one, we have 9 factors, but the 9 factors in total explain the same amount of variation in y as the one-factor model, as the factor in one-factor model in the simulation. So if you run this model with G-things, basically this is G-things, right? I talked about the naming issue, but this is essentially interactive fixed-fat counterfactual model. And if you know R, if you you use a Oracle estimator, you know exactly how many factors need to be included in the model. You have a mean square prediction error like this. Of course, with more factors, because you have to estimate with the same amount of data, you have to estimate more parameters. The errors, the out of sample errors, are bigger. And if you use cross-validated number of factors, R is the number of factors, the errors increases much faster because as you have more and more factors, sometimes with limited amount of data, sometimes the algorithm simply cannot find enough number of select enough number of factors because it cannot distinguish signal from noises, right? And if you use a matrix completion method, so the error is pretty much flat. It's fairly stable. When you have a few strong factors, it does not work as well as interactive fixed-fat model because it has biases. But as the number of factors increase, the variance increases much more slowly than the interactive fixed-fat model, especially if you don't know the correct number of factors. These are the trade-offs. But I think that they are, for a lot of social science data, they look pretty similar. For a lot of social science data, a lot of those data are driven by a smaller number of factors. Actually, G-things will work slightly better than matrix completion. Here I show you, so again, the x-axis the number of factors, and the true number of factor is 2. Two is the correct answer. In the true DGP, there are 2 factors, and this line shows the pre-treatment fitness, the pre-treatment variance of the residual or standard error of the residual. It decreases all the time, right? Because overfitting, as you include more and more factors, the pre-treatment fit will always improve. In-sample fitness will always improve, but the out-of-sample error will start to increase. And this part is biased, and then additionally, you have variance increase. So for MC, we also have a declining sigma for the fitness becomes better and better, and the in-sample fitness becomes better and better. But of course, you don't hit this. So of course, sorry, I forgot to explain. The x-axis is the log term of the tuning parameter. You don't have you do not observe a local minimum because this model, this is not a fair comparison because this model is generated by a 2-factor model. So IFE actually with 2 factors is the correct model. But with MC, because the model is misspecified, there's no, you can't find a local minimum. Okay. All right, so we haven't talked about the inferential method. We only talked about the point estimate. How can we get confidence intervals and standard errors? With large data, large meaning T and N are both large, it's doable. You can, these days there are papers on the theoretical asymptotic standard errors, especially by Professor Bai and An from Columbia. They've written several papers on the limiting theory of this estimator, including G-things, including embedding interactive fixed model in the DID setup. They've worked on this. Practically, you can use simulation-based methods to obtain standard errors, confidence intervals, or uncertainty estimates. The one method is non-parametric block bootstrap or cluster bootstrap. You sample the entire unit. Every time you sample with replacement, a set of time series. For each unit, you make the entire time series intact and then sample by time series. And it is valid when the number of n is large, and then the number of the proportion of the treated unit is fixed. And you need to have enough number of treated units. You cannot have one. If you have like one treated unit or two treated units, you cannot do this, because in some rounds of the bootstrap, you run out of any treated unit. You don't have any treated unit, then the algorithm simply cannot run. Okay, so you do want to have enough number of treated unit or treated observations. And there's another method which is a permutation based. Does not permute by n, it permute by time. Assumes it's in the sharp known or sharp knowns, essentially assuming this treatment has absolutely no effect, and also assume randomization over time. This is a pretty strong assumption by blocks. So then in the permutation, you will permute the blocks by time. You rotate blocks. One of the algorithms is to use a moving block to reassign the treatment status, and then estimate the same model, and then get the test statistics, just like in other permutation tests. It is exact if the errors are IID. It follows strict exogeneity, right? It's implied by strict exogeneity. Then the errors are IID, then you have exact inference. So you can also do that. I think in our package, both are supported. And more common, I use this one because the people are more used to inference under the weak null. Okay, right. So next, we're going to discuss diagnostic tests. These are, I think, in my personal opinion, very important for practical work.